right, page 221 in your textbooks, you had problems 14, 17, and 19. So we'll review some things we talked about yesterday. We kind of transitioned from talking about temperature, which, Audrey, what's temperature again?
Is the measurement of thermal energy.
Good, it's the amount of thermal energy in an object. How do we measure temperature? What kind of units do we use, class? Degrees Fahrenheit, degrees Celsius, Kelvin. That's thermal energy, that's thermometry, that's temperature, right? We transitioned from that to actually talking about heat. And there's a key word to remember with heat. Heat is the, what, Michael? Transfer of thermal energy from one body to another. And so heat isn't measured in degrees. Heat is measured in, class, joules is the main unit we'll use. Also, other units of heat? BTUs. Calories, right. BTU stands for anyone? British thermal unit. And what is a BTU? What is a British thermal unit? We don't use it in science anymore anyway, but just, for the record, Kendall? How do they define the British thermal unit?
Is it something to do with calories?
No, but it's got a similar definition to a calorie. Audrey?
When 1 degree of water.
A degree of water?
No. Backwards.
Smart one.
Michael?
It raises 1 pound of water 1 degree Fahrenheit.
It's the amount of heat that's needed to raise the temperature of a pound of water 1 degree Fahrenheit at normal atmospheric pressure. And calories is a similar definition, but obviously more scientific units. Does that help now, Audrey?
1 gram of water goes up a degree Celsius.
Good. The amount of heat needed to raise the temperature of a gram of water 1 degree Celsius. What about the calorie with a capital C, Kendall?
The energy content food.
That's how we describe the energy content in food, but literally what does a calorie with a capital C indicate? Like, why a capital C? What's so special about that? Michael?
It's 1,000.
It indicates it's 1,000 actual calories. This calorie is a very small unit, so a kilocalorie is indicated with a capital C. Is a joule big or small?
Small.
Very small, right? Especially when you're on a budget. You can't afford to get the big, 3 carat. Anyway, dumb joke. I'm sorry. I just came out of pre-algebra. I'm not sure why that's an excuse, but I'm going to try it anyway. So a joule is a very small unit. Do you remember how many joules it takes just to make a single little C calorie? Anyone?
4 point something.
4.184 approximately joules to make a single calorie. So a joule is very, very small, which means when we get our answers for how much heat is needed for this, how much heat is needed for that, we're going to get lots of joules, thousands and thousands of joules for many of our answers. And so a lot of times we may go with kilojoules, right, to get it in terms of thousands of joules that way. We said that if I wanted to raise the temperature of an object, maybe this bottle of water, I want to raise this bottle of water's temperature a degree Celsius. Well, the thermal energy transfer or heat needed to raise the temperature of an object 1 degree Celsius, class, is that object's... You were too specific. Heat capacity. That bottle of water has a certain heat capacity. Now, if I drank half of it, it would have a different heat capacity. If it had motor oil in it instead of water, that'd be very strange, but that would have a different heat capacity as well, right? Every different object individually has its own heat capacity, and so I said it really doesn't help to find heat capacities per se of individual objects or try to keep track of that, but rather if we went just a gram of water or a gram of a substance, 1 degree Celsius, we call the temperature, the heat needed to raise the temperature of 1 gram of a substance 1 degree Celsius, that substance's, class, specific heat. Now, for water, what is its specific heat? 4.184 joules, or a calorie, right? The calorie is the definition based on water, but other substances have their own specific heats as well. Comparatively, though, water has a higher specific heat than the other substances that we looked at, right? Not the highest specific heat of all, but a higher specific heat. Why is that beneficial being here on planet Earth? We have a lot of water, so how does water having a high specific heat help? it doesn't boil so easily, right? Now, that's frustrating when you're cooking, right? Because it takes forever for the water to boil. Because that's a lot of thermal energy transfer that has to happen to get the water's temperature up to boiling. We'll talk today about actually boiling the water. It takes a long time. But can you imagine if water boiled very easily? And so water's temperature could increase very easily? That'd be a problem, wouldn't it? Right? How many of you have a pool at your house? Swimming pool at your house? Okay, you do. If you try to go swimming in May, it's kind of chilly. June, not as bad, but probably still a little bit chilly. July, it's great. You get in the water, it's like, cool and refreshing without like freezing instantly. Like you step in, it's like, I'm going into shock, you know? And then by the end of July and early August, though, I don't really want to get in the pool. It's warm, it's not cool and refreshing anymore. Right? And it stays that way for a while too, doesn't it? Because once water has been warmed, once water has gained thermal energy, it tends not to lose it for a while. It holds on to that thermal energy. So water doesn't change its temperature easily. That's important for our climate, for the environment, right? If water changed its temperature easily, that would be a real problem. So God, again, in his providence, knowing what he's doing, right, made water have a higher specific heat than a lot of the other common substances we would see here on the earth. We talked about finding heat needed to change temperature, and we had a heat equation. And what letter did we use for heat, Kendall?
Q.
Capital Q for heat. Just cuts. And what was the equation for heat, Kendall?
C sub SP.
And we use that to notate specific heat.
M delta T.
Good. How much heat do you need to change the temperature of a body? Well, it depends on the specific heat of the body. Some substances heat more quickly. Some substances absorb thermal energy more rapidly and their temperatures go up more rapidly. Depends on the mass. The more substance there is, the more energy it's going to take to raise the temperature. And it depends on how much you want to raise the temperature. If you only want to raise it a little bit, it doesn't take as much heat. If you want to raise it a lot, it's going to take more heat. So all three of these factors come into play in how much heat is needed to change the temperature of a body. You used this equation kind of on its own for one of your homework problems last night. But then the other homework problems dealt with what we call heat exchange. What was that law of heat exchange, Audrey?
Negative Q loss equals Q gain.
Yeah, the heat that's lost from one thing will equal the heat gained by the other if the substances are isolated from surroundings where thermal energy can't escape. But since a loss is negative, we put a negative on the negative to make it positive to match heat gain. And so we worked with this equation still in kind of a subset of that equation. Let's take a look at page 221, then problem 14. Read the problem for us, if you would, Michael.
Find the amount of heat required to raise the temperature of 2 kilograms of lead from 20 degrees Celsius to 100 degrees Celsius.
All right, so maybe, the little dumbbell weights, hold them in your hand kind of thing. Maybe there's a couple of little dumbbell weights or a single dumbbell weight, for instance. It's around maybe 4.5 to 5 pounds, right around 4.5 pounds, I guess. And it's been sitting out in the sun. And so it's getting hotter and hotter and hotter and hotter and hotter. Or maybe somehow it was sitting over an open flame. I don't know. Anyway, its temperature has gone up. How much heat would it take to raise 2 kilograms of lead from 20 degrees Celsius, which is a comfortable 68 degrees Fahrenheit, to the boiling point of water? Maybe it's in a pot of boiling water then. I don't know. How much heat is needed to raise its temperature? Well, plug it in the equation, class. Say with me. Q equals C sub SP M delta T. We start by finding the specific heat of lead. And when you looked it up, what was that, Kendall?
0.130.
Yeah, 0.130 joules per gram times degrees Celsius. The mass of the lead. But remember, I said because the unit for specific heat is grams times degrees Celsius here in the bottom, our mass, class, has to be in grams. We're so used to making it kilograms, now we got to flip that on its head. So instead of 2 kilograms, class, we'll put 2,000 grams. And then for the change in temperature, if we're trying to change the temperature from 20 degrees Celsius, go up to 100 degrees Celsius, class. 80 degrees Celsius. Of course, the degrees Celsius in grams cancel with the denominator grams in degrees Celsius. And when you multiply all that out, you got a really big number of joules. How many joules, Kendall?
20,800.
And how many sig figs we allow? Looks like 3, so that's actually perfect. We can leave it that way. Or you could say 20.8 kilojoules. Either of these answers would work. Or 2.084 joules, I suppose. How many have one of those answers? For number 14? Question.
I had 200 instead of 2,000.
Oh, okay, yeah, kilo meaning 1,000 there. Quick reminder. Number 17, we use the law of heat exchange. Read number 17 if you would. I told you the container gets ignored here. Kendall?
A small
Crucible.
crucible containing 400 grams of gold is heated to the temperature of a small furnace, and then the gold is dropped into 1,000 grams of water at 10 degrees Celsius. If the final temperature comes to 20 degrees Celsius, find the temperature of the furnace. Neglect heat losses to any container.
All right, so a crucible is just a small bowl used for heating things. It's very flame resistant. And so we've got a little bit of gold here in the crucible, and it's sitting in a furnace, and then very carefully the gold is poured into, or dumped into, I guess it wouldn't be poured because I don't think gold would have been melted at that temperature, but the gold is dumped into a cup of water. It doesn't tell us anything about the cup or the container of the water. And it says neglect heat losses to any container, meaning heat will be lost to the container and then to the environment around. We're going to ignore the container completely. So there's only 2 things we have to worry about, class. The gold and the water. One of them is losing heat, class. The gold. So the gold goes on the losing side, and what's gaining heat? The water. If there were other things losing heat, we'd put those in there as well. If there were other things gaining heat, we'd put those. Suppose the entire crucible with the gold were dropped into the water. Well, then the gold and the crucible would both lose heat. Suppose we knew what the container was. Well, we'd add the container in here as well on the side that would gain the heat. In each case, though, Q class is C sub SP M delta T. So we're going to take the negative specific heat of gold times the mass of the gold times the temperature change of the gold. We're going to take the specific heat of water, the mass of the water, the temperature change of the water, and plug those things in. Let's start with the gold. What was gold's specific heat?
0.126.
Let's say 0.13 I think is lead.
Yeah.
I thought gold was a little bit different, though it was down there on the low value. Yeah, 0.126. So if you used 0.130, your answer is going to be just the tiniest bit off. The mass of the gold, we have 400 grams. We want grams, so we're happy with that. And remember, delta T is always, class, final minus initial. We know what the gold ends up at. The gold, after sitting in the water long enough, drops all the way down to 20 degrees. What we don't know is what did it start at. So since I don't know what it started at, class, I can represent that as X. Or I could leave it as T sub I. I'm a big fan of X. And so we'll have final 20 minus initial, which I don't know, we'll just call X. On the other side, we have water. Well, we know its specific heat pretty well by now. 4.18. If you want to be more exact, 4.184. Don't bother. The chart says 4.18. We're doing 3 sig figs on the other side anyway. The mass of the water. 1,000 grams. By the way, 1,000 grams is a kilogram. That would be exactly a liter of water. And then the temperature change. Well, again, everything ended up at 20, right? Because the gold and the water attained, what's that called?
Equilibrium.
Thermal equilibrium. They have the same energy level, same temperature. But if the water started at 10 degrees, which is about 50 degrees, if I think Fahrenheit. So it started at 10, went up to 20. So what's the temperature change of the water? 10 degrees Celsius. Let's see, multiply 10 times 1,000 times 4.18, and we end up with
31,800.
that side's easy. On the other side, though, because there's a binomial, I'm going to have to do what with this quantity up here? Distribute. So let's start by multiplying the 0.126, or negative 0.126, times the 400. What ends up getting distributed here? A negative 50.4, which gets distributed by the 20, negative 1,008, and the negative 50.4 gets distributed to the negative x. Be careful with your algebra. And then to solve, we're going to move the negative 1,008 over to the other side by adding it as a positive 1,008 to the 41,800. Divide out the 50.4. And what should we have gotten for the initial, that was hot, initial temperature of the gold while it was in the furnace? 849.3, blah, blah, blah. Is it 2 or 3 sig figs in this problem? Number 17, I'm seeing 3 at least everywhere, so 849, and it's a temperature we were finding. Temperature would be measured in degrees Celsius. Heat's in joules, temperature's degrees Celsius. I don't know, maybe this is the fiery furnace. It's heated 7 times hotter. I don't know. But 849 degrees Celsius should have been our answer. Did anyone have that? Okay. Audrey, were you really, really close to that?
I had 20. I didn't put 20 minus x, I just said x.
Oh, so, okay, so you said, I don't know the temperature change, you just called it x. Okay, did you, so you had a couple of issues then. So maybe, were you around 800, trying to rework the problem in my head. 870-ish? 880-ish?
Yeah.
Okay, so that accounts for, you just didn't account for the 20 minus, which you actually found was literally the temperature change. And you would have also then had a negative on your answer as well, correct? Okay, so a couple little mistakes then, but we know what you did. Kendall, Michael then, questions, comments, do we know what we did?
I read the wrong problem.
Oh, lovely, okay. That'll do it every time. Kendall?
I had the 0.130.
Oh, so you were the 0.13 person. You same as her? Did you copy off her work? All right, questions on this. Was that your only mistake? So you would have been really close to this. You'd have been like 830, something, 840, low 840s?
Yeah.
Okay, so you were really close. So just a specific heat issue then. Okay, all right, so not too bad. And then we'll never know about Michael because he did the wrong problem. All right, number 19. Go ahead and read that for us if you would, Audrey.
Lead shot weighing 810 grams at 100 degrees Celsius is dropped into a calorimeter cup containing 350 grams of water. The cup is 200 grams of copper, and both the cup and water are initially 15 degrees Celsius. What is the final temperature?
I don't know if you remember talking about calorimeters last year in chemistry class, but a calorimeter is just a specially designed device designed not to allow heat to be lost to the surroundings, so you can get really accurate measurements. So imagine we've got some buckshot shells that are broken open, and the shot is dumped into a boiling pot of water for some reason till everything attains equilibrium. So it's 100 degrees Celsius lead shot. Strain it out so we only have this, no longer the water on it. Dump it into the calorimeter cup, and of course the temperature is going to rise. So we've got 2 things that are going to gain heat here, class. The water and the calorimeter cup are both going to gain heat. What's going to lose heat? The lead, right? So for this problem, on the losing side, we have lead. On the gaining side, we have the water and the copper cup. So once again, CSP M delta T. CSP M delta T. But we also have copper. CSP M delta T. Just plug in the numbers, follow the algebra. Let's start with the specific heat of lead. We just saw it a few problems ago, and a couple of us, in fact, tried to use it again. So what do we have this time? 0.130. This time it's correct to use it. The mass of the lead, 810 grams of lead, which isn't actually that much because it's very dense, so it doesn't look like as much. And then it says the lead was at what temperature? It was at 100 degrees, and it went down to what temperature? We don't know. So we don't know the final temperature, but we know final minus initial is going to be T sub F minus 100. Does that make sense? Did we do that? Oh, okay, yeah, the 100 is what it started at, so we got to do final minus initial, that's why I emphasize this. Or we can say X minus 100. Would we rather say X, or we want to do T sub F? We like X. Children after my own heart. I say children, he's an adult. Your children. For another month and a half? 4 months? I think y'all were March. Y'all are June.
Yeah.
June babies, that's right. Okay, anyway, water. Specific heat? 4.18. How much water was in the calorimeter?
350 grams.
Only 350 grams. And the water started out at 15, but again, it rose to an unknown temperature, which again I will call. So I need to write what in here for the temperature change? X x minus 15. Then we get to the copper calorimeter cup. Well, what's the specific heat of copper?
0.39.
The mass of the calorimeter cup.
280.
And the temperature change. Well, do I know the final temperature? Once again, that's going to be x. But we knew it started at 15, so we'll also do x minus 15 here. And the annoying thing is 3 different times I'm going to have to do what? Distribute. I'm going to figure the value and distribute. Figure this and distribute. Figure this and distribute. So let's start on the losing side, the lead. Let's see. And what ends up getting distributed here?
5.3.
A negative 105.3. Obviously, if you multiply that by x, it's negative 105.3x. If you multiply it by negative 100, though, it becomes positive 10,530. On the other side, we're going to multiply the 4.18 by the 350 to get
1,463.
and that's what gets distributed. Obviously, multiply by the x is 1,463x. Multiply it by the negative 15 we get.
21,945.
Plus, now we have to just multiply the 0.39 times the 280 to get, and that gets distributed. Obviously, times the x is just 109.2x, times the negative 15 is, and there's our equation now that's going uphill. All right, questions on this? To finish it out, we got to get all the x's together. I've got an x here, and I've got a pair of x's here. Let's get all the x's on the right-hand side so we don't have to deal with negatives. Make sense? So we'll take the 1463x plus the 109.2x plus what will be a positive 105.3x to get how much x on the right-hand side? 1677.5x. Now let's take these two negative values, move them over to this side with the 10,530 to get a big positive number. And what big positive number should we have on the left? To finish, we simply and we get what for the final temperature of the cup, the water, and the lead?
20.331.
Is it 3 sig figs in this problem? Number 19, right?
Yes.
I got 3 everywhere, so
20.3.
and it's a final temperature I'm finding, so we'll put that in degrees Celsius. Again, heat in joules for our purposes, temperature degrees Celsius. Didn't look like anyone was on the right track with that one because of the binomials. Does it make sense though? And that's why we've got to remember change in temperature, final minus initial. If there's one of them I don't know, call it x. If you do know it, plug it in, and obviously if you know both of them, you can just subtract to get a nice easy number. You're going to have another one of these. No, we won't have it for homework tonight. But tomorrow we'll practice with another one of these. All right, questions on this? All right. Now, we talked about changing the temperature, right? So for instance, we even mentioned with water, it takes a long time for water to boil. Put it in the pot, turn on the stove. Gas stove will heat a little bit quicker, but right now, have you heard all the hate the gas stoves are taking on the news? Oh my goodness, gas stoves are dangerous for everybody, and gotta get rid of them. And of course, all the people saying you gotta get rid of them have gas stoves themselves, and they're not gonna give them up, but you have to give them up because they're dangerous to you. You don't even know how to handle this. Anyway, typical hypocrisy. But anyway, getting off of that. But you put the water on the stove to boil, and you wait and you wait and wait, and little by little, thermal energy is added, transferred, gained, if you will. Energy levels higher and higher, temperature higher and higher and higher, and you're watching the little thermometer, you're dipping it in the water. 97 degrees Celsius, because you're cool like that. You do stuff in Celsius, 98. Okay, you're not. You're doing Fahrenheit. 198 degrees Fahrenheit. 203 degrees Fahrenheit. 210 degrees Fahrenheit. Like, it's so close, so close. And then 212 degrees Fahrenheit, what happens to water? It starts to boil, right? It gets to the boiling point. What doesn't happen is 210, 211, 212, and it all vaporizes. That doesn't happen, does it? What happens is it stays at 212 for a long time. And little by little, more and more of it begins to boil away. Now, in reality, what's going to happen is, as it boils away, it becomes steam, which turns into water vapor, which condenses on stuff and whatever, but it becomes steam. And but it doesn't instantly all become steam right away, does it? Individual molecules, water molecules that have enough energy break free. Remember, the molecules are moving faster and faster and faster, and a few of them have so much energy, they break free and go into the air as steam. And little by little, more and more of them begin to escape into the air as steam. What about if you put something in the freezer, right? Put it in the freezer, and the temperature begins to drop, drop, drop. Kind of like outdoors in a winter day, right? The temperature goes down, temperature goes down, temperature goes down. As the temperature falls at 32 degrees Fahrenheit, since we're in the US, 0 degrees Celsius, what begins to happen to water? The energy level of the water gets lower and lower and lower and lower until eventually it goes crystalline into ice. Now, at 32 degrees, does all the water instantly become ice? No. Gradually, molecules come together into that crystalline structure as their energy levels drop, and it becomes ice. Or if you took an ice cube out of the freezer and you set it on the counter, what happens to the ice cube? Gradually, it melts. Now, as it melts, it sits in a little pool of its own water, right? And because the ice and the water are touching each other, one presumes they would be at thermal equilibrium. What you have then is 32 degree Fahrenheit water and 32 degree Fahrenheit ice right next to each other. Why is some of it ice and some of it water? Well, some of the molecules, their energy level is still such that they're still in that crystalline structure. Some of them, the ones on the outside that have been exposed to the air, their energy levels have increased as they absorbed thermal energy. They've gained heat, if you will, and so their structure's broken down and they've become free-flowing water. Here's the point. Both of them were at the same temperature. They both have the same thermal energy in the sense of their temperature, yet some of the molecules had more thermal energy that didn't even change the temperature, but it changed the state of matter, or the phase, if you will, of matter that the water was in. Does that make sense? So we want to look at this idea of phase changes. Phase changes. And we're going to look exclusively at water. Obviously, other molecules, or other substances, I guess I should say, can experience phase change as well. Water is readily available on our planet. We're going to deal with water. As I said, at 0 degrees, you could have either ice or water. You can have 0 degree water. It doesn't instantly turn to ice, but gradually, as thermal energy is taken out, right, the crystalline structure is formed and we get ice slowly and gradually. Or ice at 32 degrees begins to start melting. As it gains thermal energy, it will begin to break down that structure and turn into water. At 100 degrees, you can have 100 degrees Celsius water, you can have 100 degrees Celsius steam. What makes the difference? Which individual molecules have gained enough energy to vaporize? Or at 100 degrees, vapor could turn back into water if the energy of those individual molecules decreases. There's additional thermal energy at 0 needed, not to suddenly change the temperature, right? You keep adding, for instance, you put an ice cube into a pot on the stove, okay? It'll rapidly break down, right? But it's not changing the temperature until the water has, for instance, you've got the little ice cube in there, and if you touch the pan, you're in trouble. But if you touch the water would still be 0 degrees right around that ice cube, until eventually the whole ice cube is melted, and then the temperature can begin to rise. Does that make sense? The water molecules have to gain additional thermal energy to change from one state of matter to the other. We call this heat that doesn't cause a temperature change, but rather a state change, as latent heat. Latent heat. Latent heat is heat absorbed or released that does not change temperature. Heat absorbed or released that does not change temperature, but rather contributes to a phase change. Heat that doesn't cause a change in temperature. 2 types of latent heat. First of all, we have what's called the latent heat of fusion. The latent heat of fusion. When you hear fusion, think melting. The heat needed to melt something. And every substance has its own melting. Well, I shouldn't say every substance. A lot of substances out there have their own melting. Well, you can melt gold, right? You just have to get it hot enough. Add enough heat to gold, and you can melt it. Gold has a heat of fusion. Well, water does as well, or ice, I should say, does as well. There's a latent heat of fusion. There's another type of latent heat called the latent heat of vaporization. The latent heat of vaporization. That one kind of is self-explanatory. You vaporize, right? You evaporate, if you will, and turn, in this case, water into steam. Now realize, latent heat in this sense is heat that must be absorbed by the water or absorbed by the ice to make it melt or make it vaporize. But you realize from the other side around, you could have heat that is taken out of water that causes it, instead of melting at 32, you take the heat out, and that's what a freezer does. It sucks the heat out of everything and causes it to freeze. So freezing would be negative fusion, if you will. Negative fusion, that's freezing. What do you think negative vaporization would be? Instead of evaporating the water condenses, right? So the condensation is negative vaporization. Freezing is negative fusion. We're going to be looking at it from the perspective, though, of adding thermal energy to the water. So we're going to look at it in these senses. You need to know a couple different things. First of all, latent heat of fusion, we'll notate L sub FUS, is 333 joules per gram, again, for water. Every gram of ice has to gain an additional 33, or there have to be an additional 333 joules for every gram of ice in order to melt the ice at that freezing/melting point. Why? Again, you have to add enough energy to cause the thermal energy levels to rise, to break down that I'm staying in this crystalline hexagonal structure to I'm freely flowing now. We haven't changed the temperature, but we're changing the energy level. Heat of vaporization, L sub FVAP, heat of vaporization is much higher. Because remember, water has rather strong cohesion. Adhesion is stronger than cohesion, but water has a strong cohesion. Water molecules tend to stick together. You're literally taking a molecule and causing it to go flying up into the air, leaving everyone else behind. Now again, the water as it moves, the molecules will move faster and faster and faster inside that pot as you raise the temperature. But at the boiling point, as you're trying to vaporize the water, you've got to give enough energy that no longer are they just moving around quickly where there's still some cohesion, they actually leave the pot. They leave all the other water molecules behind and go flying up into the air. So it's going to be a lot more, 2,260 joules of latent heat needed for every gram of water that you're trying to vaporize or boil. 2,260 joules per gram. I believe you used this process last year in chemistry, so if this seems somewhat familiar, it should. Let's take a look at a problem here. Let's suppose we had a 25.0 gram ice cube. And suppose it's sitting in the freezer, and most freezers aren't exactly 32 Fahrenheit. Usually they're colder than that. Let's suppose it's at negative 10.0 degrees Celsius. So we have a 25 gram ice cube. The freezer happens to be negative 10 Celsius, which is about 14 degrees Fahrenheit. That's somewhat realistic for a freezer, or maybe a deep freezer. Let's suppose, and this will take a little bit of a stretch, but I want to show all the different phases of this. Suppose we wanted to get superheated steam. Now, reality. You boil water, steam rises, and immediately, once it leaves the pot, there's nothing to continue heating it, right? So it will condense on stuff, right, as it cools back down. But let's suppose we were in like a steam room. You know what a steam room is? Right, where they can actually, the room itself gets heated as well to keep the steam in the air, so to speak. Let's suppose we have some kind of chamber into which we're heating this, where the chamber can continue to heat this steam even while it's in the air. We can heat it even hotter somehow. Let's suppose we want to turn this ice cube into 120 degrees Celsius superheated steam. All 25 grams of it. So we start with 25 grams as a little block, then it turns into free-flowing water, and then it turns into steam in this chamber in which we're heating it. Make sense? Well, you can't just boom ice into steam, right? At least not regular water ice, right? There is that, remember what dry ice? It's some kind of, I actually forget, what is dry ice? Do you remember from last year? It's a nitrogen compound, right? That it doesn't evaporate. Do you remember what we call it when it goes straight from the solid form to the gaseous state? Sublimation, I believe, right? It sublimes into the vapor, which is really cool, right? Because you put it around and it makes this weird, misty vaporizing. And The problem is it's toxic, so you don't want to hide down low behind because you're inhaling it all. And I think some kids died playing with dry ice at Halloween one year. They were hiding behind some stuff with all the dry ice around them, so all this steam's rising. It's really creepy and eerie, but they inhaled too much and it killed them. Anyway, so be careful with dry ice. Dry ice is cool for all kinds of things, blowing stuff up. Did you do any of that last year in chemistry? Shake up a bottle with dry ice in it, and the vapor builds the pressure, right, and it blows up. And we had a kid we had a kid one year. The science teacher's kid, actually, she brought in a container, little bottle. But you remember this?
I don't know. I think
you might have heard of it. I don't know. I think this was before your time. Mrs. Harmon.
Mm-hmm.
Shout out to Mrs. Harmon.
Yeah.
But she had a Gatorade bottle, put some dry ice in it with some other water, which immediately caused the water to start boiling. And but the pressure got mounted, and the idea was you chuck the bottle, and the bottle explodes.
Mm-hmm.
And you don't want it exploding right next to you. Well, apparently it didn't explode. So her son went over and he's like, "What's wrong with this?" Or maybe, no, I don't think it was, maybe it would have been his friend Tyler. Anyway, somebody went over to look at the bottle and see what happened, and when he touched it, it exploded, and shards of plastic Gatorade bottle cut him.
Mm-hmm.
And it was a bad day. Anyway, I think he was told not to go over there, so I think he was disobeying at the time, if I remember the story right. I was not there. I got it all secondhand. It was one of those, well, that'll learn you. Anyway, but ice doesn't go straight into steam, right? In order to turn ice to steam, we first have to turn ice into water. But you can't turn ice into water if it's at negative 10 degrees Celsius, can you? So what we're going to have to do is take the negative 10 degrees Celsius ice and turn it into 0 degrees Celsius ice. Does that make sense? We have to add enough thermal energy to change the temperature of the ice to get it to the melting point. Make sense? And then once it's at the melting point, does it instantly melt? No, it slowly melts as more thermal energy is absorbed, right? So what we have to do is take the 0 degrees Celsius ice cube, and as it sits there in whatever container we're heating it, it has to turn into 0 degrees Celsius water. Does that make sense? Once it is all melted and it's all water now, we can then change our water, nope, not directly into steam. We have to get the water's temperature up, don't we? Water can't turn into steam if it's still at 0 degrees. What temperature do we have to get the water to? 100 degrees. So we need to take our 0 degrees Celsius water, and we have to raise the temperature to 100 degrees Celsius. But it's still going to be water at that temperature. Does that make sense? Because as soon as it hits the boiling point, it's not that, boom, it all vaporizes instantly, does it? You get it to the boiling point, and then gradually, as more thermal energy continues to be added, the temperature doesn't go up, but the energy level does. This latent heat is added, and we can take our 100 degrees Celsius water, and if we wait long enough, and we just keep adding more heat, we can get it up to 100 degrees Celsius steam. Make sense? So now the steam is in the chamber at 100 degrees, but we want to continue adding more heat to raise the temperature of the steam, because we want superheated steam at 120 degrees. So we can take 100 degrees Celsius steam, and we can turn it into 120 degrees Celsius steam, and our objective is accomplished. But it took 5 stages of adding heat, 5 different sets of heat, if you will, that are continually added more and more to go from super frozen ice to the freezing point, or, well, freezing point, melting point. Then you have to melt it. That's not a temperature change. That's a phase change. Then you have to raise the temperature of the water that you have. But then the water has to turn into steam. That's not a temperature change. That's a phase change. And then if you wanted to superheat it, you would change the temperature again. Does that make sense? For every time the temperature changes, it didn't change states of matter here, or here, or here. Every time there is a temperature change, write this in your notes. Temp change, you're going to use Q equals C sub SP m delta T. That's the equation for finding heat needed to change a temperature. But every time there is a phase change, well, I wouldn't use that equation, would I? Because that equation revolves around a temperature change, and there is no temperature change from 0 degrees Celsius ice to 0 degrees Celsius water. There is no temperature change from 100 degrees Celsius water to 100 degrees Celsius steam. It's a phase change. It's latent heat that's needed. So in those cases, heat will be calculated by multiplying the latent heat times the mass. The latent heat, 333 joules for every gram. Okay, multiply that by the 25 grams you've got. 2,260 joules per gram. Okay, multiply that by the number of grams you've got. And that tells you how much heat was needed to change the phases. Make sense? Let's do this then. Let's take our negative 10 degrees Celsius ice and turn it into 0 degrees Celsius ice. That's a temperature change, so what equation do I use, class, for part 1? CSBM delta T, okay? Now this is ice. Ice has a different specific heat than water does, than liquid water does. Flipping back, I think it's page 214. What is the specific heat of ice?
2.05.
2.05. The mass of the ice, we said, is a 25 gram ice cube. And we want to change the temperature how much to get this ice cube to the melting point? 10 degrees. We want to go from negative 10 to the melting point. We multiply those numbers on your calculator. And we get
512.5.
That's not that many joules just to get it to the melting point. By the way, you may have noticed it doesn't take that long if you take an ice cube out of the freezer and set it on the counter to see it start melting. It'll take a little while to melt it. Once it's at this 0 degree melting point, we have to melt all of that ice into water. Again, the ice is sitting there amongst other water. It's all at thermal equilibrium, so it's all at 0 degrees. It's just different energy levels visible. You see high energy water and low energy ice touching each other. That's a phase change that's about to take place. So to find a phase change, class, we multiply latent heat by mass. In the case of melting the ice, that's the latent heat of fusion. So we'll multiply the latent heat of fusion times the mass. What was that number? I had to erase it to make room to work, but what is the latent heat of fusion? 333 joules per gram, and we're going to multiply that by the number of grams, 25. How much heat is needed to melt all of that ice?
8,325.
1,000? 8,000. Say it louder.
8,325.
8,325 joules. That's a lot more energy needed. So, of course, that's going to be a slower process. You're going to see that one take longer. Now, once the water is melted, it's all 0 degree water now. Now we're able to start raising the temperature of the water because it's all actually water. So phase 3, or step 3, is to take our water and raise its temperature up to 100 degrees. That's a temperature change, so what equation do we use? All right, so now we're to liquid water. What's the specific heat of liquid water? Our old friend, 4.18. Still 25 grams of it, but now what temperature change are we trying to accomplish? We're trying to go from the 0 degree melting point to the 100 degree boiling point, 100 degrees. So how much thermal energy is needed now to raise, or how much heat is needed to raise this temperature?
10,450.
We have to transfer 10,450 joules more energy to get all of this water to the boiling point. Now it's not all boiling yet, but it's the right temperature. We're not vaporizing it yet. It's at the boiling point, and now we have to add more thermal energy. More heat must be transferred in order to get this water to leave the pot, right? To get all of it to leave the pot. So, let me work this way. Step 4. I'm not changing the temperature. As it leaves the pot, it's 100 degrees. As it's in the pot, it's 100 degrees, right? I'm changing the phase. So I need to add, class, latent heat of vaporization, right? Latent heat of vaporization times the mass. So that's 2,260, you said, joules per gram, times 25 grams of liquid water. That's not that much, by the way. How much heat has to be added to the pot to cause the last drop of water to evaporate?
56,500.
56,500 joules? And now it's evaporated into this chamber we've been using this whole time. And but we want to superheat this steam, so it's all steam now. Well, we want to raise the temperature of the steam. That's a temperature change, not a phase change. So back to Q equals? And so we take the specific heat of steam, which is different from the specific heat of both water and ice.
2.08.
And we still have 25 grams of steam floating up here in the chamber, right? But we want to raise the temperature of the steam 20 more degrees. So, how much heat is needed to superheat the steam? 1,040 joules. So the question is, to go from a 25 gram ice cube at negative 10 degrees Celsius to 25 grams of 120 degrees superheated steam in the chamber, how much heat's needed? Well, first this, then this, then this, then this, then this. What do you suppose we'll do? Add them all together. How much total heat was needed to accomplish all of this?
76,327.5.
And we'll round off to 3 sig figs based on the original numbers.
76,000.
Or 76.8 kilojoules needed to turn that little 25 gram ice cube into superheated steam. Do you vaguely remember doing this last year in chemistry? Not so much? Okay. Well, anyway, we'll work on this in the next lesson. Of course, we won't necessarily always have to change deep frozen ice into superheated steam. We'll do more with this next time. Do you have just a few pages I need you to read and a few questions I need you to answer so you'll be prepared for tomorrow? I need you to read over pages 216 to 220. Read over pages 216 to 220. And on page 221, if you'll answer questions 29 to 31. Page 221, answer questions 29 to 31. Don't bother with complete sentences since it's a Wednesday night, but I do need you to look that over so you're prepared for what's coming in our next lesson. All right, have a wonderful rest of your day. You are dismissed.